Welcome to the course Formal Language and Automata Theory. In this lecture, we are going to discuss about pushdown automata. See the contents of pushdown automata. So here we will discuss about the following concepts related to pushdown automaton. First, we will see the definition of pushdown automaton, then the languages of pushdown automaton, then equivalence of PDAs and its grammar, context-free grammar, then acceptance by final state and acceptance by empty stack, then deterministic pushdown automaton, which is abbreviated as DPDA, similar to deterministic finite automaton. Then we will see the equivalence of PDA to grammar and grammar to PDA. So here, for any context-free grammar, how to construct its pushdown automaton. Then reverse, for given pushdown automaton, how to construct its context-free grammar. These are the various topics we are going to cover in pushdown automaton. In this lecture, we will discuss about the following concepts. First, we will see definition of pushdown automaton followed by its model introduction. Then languages of a pushdown automaton. With that, we will see how to accept a language by considering the two cases, acceptance by final state and acceptance by empty state. We will see these conditions followed by example problems. Now let us see the introduction to pushdown automaton. So pushdown automaton is a type 2 acceptor as per Chomsky hierarchy. So PDA is type 2 acceptor or recognizer. So PDA accepts context-free languages, abbreviated as CFL, and its associated grammar is context-free grammar, so denoted as CFG. So by default, pushdown automaton have non-determinism, that is non-deterministic pushdown automata, which is termed as NDPDA or simply NPDA. So this also separately we will discuss. Then see the computational power of pushdown automata. As for Chomsky hierarchy, you can see the computational power is listed in the increasing order. For type 3, that is for finite automata, having least computational power, then type 2, type 1, type 0. So here finite automata is type 3 acceptor, pushdown automata is type 2 acceptor, linear bounded automaton is type 1 acceptor, whereas Turing machine is type 0 acceptor as per Chomsky hierarchy. So for Turing machine having highest computational power than previous 3 models. Those are all linear bounded automata, pushdown automata, and finite automata. Whereas finite automata having least computational power than the other 3 models, that is PDA, LBA, and Turing machine. Whereas PDA having highest computational power than finite automata, but least computational power than the remaining 2 models, that is LBA and Turing machine. Whereas linear bounded automata having highest computational power than finite automata and PDA, but least computational power than Turing machine. Like that, the hierarchy will be followed. Same thing given here, you can see computational power is higher than finite automata and lower than the remaining 3 models, that is linear bounded automata and Turing machine. So pushdown automaton has infinite auxiliary storage, which is called as memory, that can be organized by using a stack. The stack principle is last in first out, which is also called as pushdown storage. So the difference between finite automaton to pushdown automaton is, the finite automaton we don't have storage, so only partial storage. The tape will act as the storage, that is only temporary. So, but in PDA, it has infinite auxiliary storage. This can be organized using stack with the principal last in first out, which is called as push down storage. So that is the difference between finite automaton and push down automaton. The model also, this stack is additionally added, remaining all are same as finite automaton. Now let us see the model of push down automaton. You can see this diagram and compare with finite automaton. Everything same except the stack. That is the only difference. So remaining all are same. So same as finite automaton, here also you can see the PDA consisting of input tape is one component, then read head or tape reader is another component, then finite control or CPU is the another component, then output is another component. See, these 1 to 4 components are same as in finite automata. The only additional component included in PDA model is stack, which is called as push down storage. So that's why PDA contains infinite auxiliary storage, which can be organized by using stack. So remaining the purpose of each and every component and the functioning also same as finite automata. Now additionally here stack is considered. That is the only difference. So initially stack contains a start symbol which is labeled by Z or Z0, where Z0 is the initial symbol of the stack or start symbol of the stack. So then here the change of state depends on, in finite automata, a change of state may occur by seeing the current input symbol on the input tape and the current state of finite control or CPU. Then it may or may not changes the state. But here in PDA, in addition to these two, it includes stack contents also. So the change of state it depends on not only the current input symbol on the tape and current state of the stack, I mean finite control or CPU, and also the top of the stack. So this is top. So here whatever the symbol, so it depends on the top of the stack also. That is the another difference between finite automata model to push down automata model. So by seeing that, here you can see the explanation is given, whatever I explained. So PDA will have input to tape is one component, finite control is another component, and stack is another component, and read head or tape reader. In PDA, the finite control is same as finite automata with some additional computability. So because of that stack, here the state transition takes place not only on the basis of current input and current state, but also based on the current symbol. This is very important. Current symbol which is available on top of the stack. Just now whatever I explained. So this point keep in our mind in PDA. So finite control consists of different types of states. The first type we will call it as input state. Then other category is called a set of transition states. And the last category set of final state. So here we have three types of states are included in finite control. Input state, that is starting state or initial state. Then from initial state to moving to other states, except final state. Those are all called as transition states. Then other category is final states. So finite control consisting of three categories of states. Now let us see the formal definition or mathematical definition of Pushdown automata. You can recall once the finite automaton definition. So here I am writing the definition of finite automaton. Finite automaton M is a 5 tuple or quintuple which is denoted by M equal to Q sigma delta Q naught F. See 1, 2, 3, 4, 5 tuples. Whereas PDA you can observe here. So PDA also denoted by M equal to, so Q is same, sigma is same. Now here one more new tuple is added that I will tell. Then delta is same, Q naught is same. Then one more new tuple is added here. Then F is same. So here extra two tuples are added in pushdown automata. So what are the two tuples? Here you can see the extra tuple here we will call it as tau. Here you can see tau is the new tuple. Then another new tuple before final state Z naught. So this is the only difference. So here tau and Z naught are two extra tuples. Remaining all 5 tuples are same as in finite automata. Now you can see the definition. A PDA M is 7 tuple defined by M equal to Q sigma, tau is new tuple. Now delta Q naught, Z naught is also new tuple by comparing to final state. Then F is same as in finite automata. Now the meaning is same as finite automaton except the two new tuples where Q is non-empty finite set of states. Sigma is input alphabet, same as in finite automata. Then Q naught is in the set of states capital Q, that is Q naught belongs to Q, which is called as initial or start state. Then F is also same as in finite automata, which is subset of Q, which can be written as F is subset of Q, is set of accepting or final states. So before defining delta, delta is also meaning is same, transition function or moving function. See the new tuples meaning. So the first tuple is tau, which is called as stack alphabet. So all the stack symbols which are stored on stack, those can be denoted by using tau, which is called as stack alphabet. Then the stack contains initially Z naught, which is called as start symbol or initial symbol of the stack. So Z naught is in tau, that is Z naught belongs to tau, but Z naught is not in sigma. This is not input symbol, this is stack symbol. Both are different, sigma and stack input, that is tau. So Z naught belongs to tau is a particular stack symbol, which is called as start symbol of the stack. Now in delta definition, we can include the tau also. Now you can see delta is a mapping function or transition function, which is mapping from. Here you can see. Before now you can see the finite automaton delta is defined as by seeing the current state from Q and current input symbol from sigma, it gives what is the next state. So this is the delta definition of finite automata. Whereas PDA you can see. Here also it takes the state from Q cross, then sigma. Here sigma also includes null also, but null not is in sigma, but the transition with null also is allowed in PDA. But in finite automata also allowed, but that is non-deterministic finite automata with epsilon modes. But normal finite automata does not contain epsilon directly. But PDA in the introduction we saw one point. By default, PDA is non-deterministic. So it has non-determinism by default. That means it allows the transition with null also. So Q cross sigma union null cross. Here additionally you can take the stack alphabet tau. So three parameters we have to consider for the current transition. So that is Q sigma union null cross tau. Then it gives the next state as combination of Q cross tau closer. Here what is tau closer? Tau is stack alphabet, whereas tau closer is string of stack contents. Combination of one or more symbols from stack. So here that is the difference. So in finite automaton, see let us see a transition. Suppose a state Q naught on input A, it gives only one or more than one next state. But in PDA you can see. In PDA it is different. So here you can take Q naught, then input symbol, then it takes stack symbol also. Additionally, three tuples. In the delta function, left hand side it has three tuples equal to. Then right hand side what it gives next state. Suppose it may be Q1. Then tau closer, the stack contents. Suppose initially stack contains Z naught. Now A is added on top of the stack. So now here A will be placed before Z naught. That means it will be placed on top. This is the format of transition function of PDA. That is the difference here. So now by seeing this definition, now let us see one important representation of PDA transitions by using the concept of instantaneous description, which is abbreviated as ID of a PDA. So the instantaneous description is used to represent the moves or transitions in PDA. Now, how to define this instantaneous description of PDA? Now, let us see the definition. So, let M equal to Q sigma tau delta Q naught Z naught F be a PDA. Now, wherever PDA occurs, you have to remember the 7-tuple definition. Whereas finite automata, the 5-tuple definition. So now PDA means 7 tuples. Additionally, tau and Z. So now let M equal to Q sigma tau delta Q naught Z naught F be a pushdown automata, and instantaneous description is defined as a triple combination of 3 tuples. The first one is Q, second one is W, third one is gamma, where the first one small q belongs to the set of states capital Q, then second one W, which is a string taken from the input alphabet sigma, that is W belongs to sigma, then third one gamma is also a string, but it consists of stack symbols, that's why gamma belongs to tau. So now here you can see the delta definition. This is capital Q cross sigma, cross sigma, then cross tau. So it takes in the delta function the left hand side 3 symbols. So this combination we will call it as a triple. So this is called as instantaneous description of a PDA. So in PDA, the moves are transition from one ID to another ID. That means one instantaneous description to other instantaneous description will be denoted by the pipe symbol. So this symbol is called as pipe symbol. So one ID to another ID, we will use this one. So here, remember one note, the ID, which is denoted as a triple Q, W, gamma, represents the current state Q, the current input symbol W, and top symbol of a stack gamma. Here, say here I already written the same. So Q cross sigma cross tau. That means from Q it takes only current state. From sigma it takes current input symbol. From tau, it takes only the top of the stack. Every time the ID takes the current symbols from all these three tuples. This is called as ID. Now let us see one example here. So if m equal to q sigma tau delta q naught z naught f is a PDA, we say the ID, now you can see q aw comma z alpha. This is left hand side of the ID. So which is combination of, here you can see it has first is q, the second is sigma, the third one is tau. So then this is equivalent to this 5 symbol, sometimes will also called as equal. But wherever ID comes means you have to use this 5 symbol. So equal to, now what is the next move by seeing this one? So the next move depends on the current state in Q, the current input symbol from sigma, the current top symbol from the stack. Now here it considers the current state is Q, current input symbol is A, current stack symbol on top is Z. So by considering these three, so the next move is, let us say, if the state is changing Q to P, now the input is after reading A, the remaining input is W, then the top symbol Z is replaced by some other symbol, that is beta. Then the initial symbol alpha remains same. So when this will happen, if there is a transition like this, so delta of Q A Z contains P comma B beta. This is nothing but, see, this is the transition. Delta of Q comma A comma Z equal to P comma beta. So now here you can observe from the current state Q, current input symbol A, current top symbol tau, the next move is P comma beta. That means Q is changing to P. So now earlier here we have Z. Z is replaced by beta. So then you can substitute these values in ID only. Now the new state is P. The remaining input is W after reading A. Then Z is replaced by beta as per this transition. Then alpha remains same. So in the PDA design, by using this ID, you can define the transitions in this fashion. Now let us see one example of a pushdown automata. So here the PDA will be given like this. Let m equal to q sigma tau delta q naught z naught f is a PDA where the tuple values are given for all the tuples. Q equal to the states q naught, q1, q2. Three states are given. The input alphabet sigma is a comma b. The stack alphabet tau equal to a comma z. See, sometimes the inputs may also occur in tau also. But remember one important point, Z naught, the initial symbol of the stack that should not included in sigma, input alphabet. But sigma includes in stack. But stack initial symbol can't be included in sigma. Here see, the input symbol A is also included in stack symbol also. But here no confusion. The stack symbols will be placed in the third position of the triple. That is after input symbol on stack only. But right side of the move, it contains only state comma stack symbols. No concept of input from sigma on right side of the move. So that's why no need to get any confusion. Now the final state is given here Q2. Q2 is the final state and delta is given by the transitions. See, all the transitions in PDA will be like this, in this format only. Any transition which is combination of a state, input symbol sigma, including null also, then stack symbol tau. The left hand side of the move equal to right hand side, what it contains is state followed by stack contents. So tau closure. So this is our delta definition. You can remember the transitions are similar to the delta definition of PDA. In the same order you have to represent. Now the first transition is delta of Q naught on input A on stack initial symbol Z naught equal to, so the change of state. Here it is going to same state, that means loop. Then the stack contents are the symbol, the input symbol A is inserting on top of the stack. So diagrammatically here you can see initially this is stack. The first move here what we have done, so we have inserted a symbol A onto the stack. Now this is the stack after inserting. In stack the insertion will call it as push operation. So here A is pushed on top of the stack. Now this is top of stack. So like that every move you can see what stack contains. The next transition you can see delta of Q naught. Now again your input is A. Your tax top top of the stack is A now. Here you can see what is the top of the stack here, A. So again what we are doing, we are inserting another input. Now the stack becomes, now you can see already initial symbol Z naught and top is A. Now you are inserting another input with same input symbol A. Now this is top of stack. Now what stack contains A. So whenever you can insert A on top of the stack, already one A is there. Now this is the new input symbol added on top of the stack. So for every move you can represent in the form of stack. Next you can see Q naught. Now input is B. Now the top is A. Here what you are doing, what is the next move? The state is changing Q naught to Q1. Now you can see the top of the stack is replaced with epsilon. This is nothing but erase. So erasing top of the stack, which is nothing but pop. Whereas these two operations we are inserting, so is called as push operation. Now here, after inserting B on top of the stack, now you can see, so here Z naught A. So now we are inserting one B. So with the input symbol B, the current top will be erased. Now your stack becomes Z naught A. So here pop A from the stack with input symbol B. Next you can see now you are at Q1 state. At Q1 again, if we have another input with B, now remaining top of the stack is A. Now here A is there. So now here, so whenever you are inserting another B on top of the stack, now this is also erased with the top of the stack. So now without changing state, simply Q1 epsilon means here erase. Now what is the stack now? Now stack contains only initial symbol. Now you can see your stack is, your current state is Q1 now. Your input is empty now. Further no input is there. Now what initial stack contains Z0. So in this case, here input is empty. Then stack is also empty. When you can say stack is empty, by saying Z0, initial or start symbol of the stack. Now it goes to Q2. Here, what is Q2 here? Final state. So then the stack contains empty now, null. So this is the final step of any PDA transition. This last step is common for all problems. For any language, you are constructing a pushdown automaton. The last step is called as acceptance step. So this is the example of PDA and its representation using stack and the meaning of the transition function. Now similar to finite automaton, the pushdown automaton also we can represent graphically using the same concept as transition table and transition diagram. So the concept is same, but the representation is somewhat different. Here we will use the same representations, transition table and transition diagram. You can see the previous example. So how to represent in the form of transition table. First, here you can take states, first column. Second column, you can take input. So one by one, you can take. Third column, you can take stack symbols. Then last column, you can take the moves. Here the moves, you can take directly from the right-hand side of the delta function. The right-hand side of the delta function, what it contains? Q cross tau closure. This as it is, we can take from the transition. So now you can recall once the previous example. Now see how the table is constructed. So simply you can take each and every move. What is the state? What is the input symbol? What is the stack symbol? From the left hand side of that move. Then in case of moves, you can write completely the right hand side values. Now see the first transition. So here delta of Q naught, that is the current state. Input symbol is A, stack symbol is Z naught. So you can substitute same values in first, second, third columns. Right hand side you can substitute directly Q naught comma A Z naught, entire moves including brackets. Now you can see the first column state in that move. So here you can write the transition clearly, you will understand. So delta of Q naught A Z naught equal to Q naught comma A Z naught. This is the first transition. So Q naught you can include in the first column of first row. This is Q naught. Then the input symbol you can include in the second column of first row. Then Z naught you can include in the third column of first row. See as it is. So we have included equal to right hand side what it contains Q naught comma A Z naught. That as it is you can write here. So simply like that we can represent all the transitions in the form of transition table. Similarly, second one you can see Q naught AA equal to Q naught AA. So here Q naught AA. The next move is Q naught AA. Similarly, another one you can see Q naught BA. So here Q naught, this is the state. Then input is B, stack top is A. The next move is Q1 comma epsilon. As it is, we can write here. Similarly, next one Q1 BA, Q1 epsilon. Next Q1 epsilon Z naught, Q2 epsilon. Like all transitions from the given PDA, you can represent by using transition table. Now, similarly, construction of transition diagram. So transition diagram construction is also same as finite automaton, but the transitions representation is slightly changed. Here you can see the states as usual. You can represent using circle. Then final state is represented with double circle. Same concept as in finite automaton. So this is the final state. Here also more than one final state exists. Whatever the final state, all you can include within double circle. Then initial state is prefixed with an arrow and also labeled with starter. So this is called as initial state or start state. This is also same as in finite automaton. Then the transitions you can see. The transitions also same, but here it includes the stack contents also. Here you can see, first let us take one transition here. Delta of Q naught A Z naught equal to Q naught comma A Z naught. See how this transition is added. In transition diagram, you can see your current state is Q naught, next state is Q naught. So it is going to Q naught itself, that is loop. So that's why here we have included as loop. Loop. Now what is the input here? A. So as usual, you can include this one, input as A. You can include the stack symbol also in the left hand side move, whatever the symbol separated with comma. So Z naught. So this is the symbol after input. Then by using R symbol, the right hand side stack contents, that is tau closure. all you can include whatever in tau closure, all you can include what tau closure contains a z naught. So here we have included a z naught. So now here you can see the first one is called as tau, the second one is called as tau closure. Tau by tau closure separated with R symbol. So you can labeled in the transition input followed by tau closure. So that is the only difference. Next, the second transition you can see similarly delta of q naught a. Now the stack is also a equal to, now here you will get q naught a. Here you can say that second transition. So q naught a equal to q naught a. Again it is going to same state only loop. So now already one loop is there. In the same loop, you can include another transition value. See like this you can see top or bottom wherever you can include. Now the input is a, here a. The stack in the left hand side of the movie is a. So a by right hand side of the stack contains tau closure. That is a. So like that any transitions from same state with the different inputs. So you can include like this. So then another transition you can see delta of q naught input b, the stack top is a. Now it is going to q1 state. Now it is erased. Now you can see q naught to q1, the transition path you can draw. Q naught to q1 state. The input is b, here b, comma the stack in the left hand side is a, or the right hand side what tau closure contains epsilon. So like this. So like this, we can include all the transitions in transition diagram. Then remaining all are same as in finite automata. Only the transitions you can include input, comma stack before after, separated by R symbol. That is the only difference. Now let us move to our next concept. The languages are accepted languages of Pushdown automata. Similar to finite automata, so every automaton it accepts its associated language. Finite automaton accepts only regular languages. Then from regular language, what are the strings derived? Those strings also accepted. Similarly, pushdown automaton also. Pushdown automaton accepts only context-free languages. Then what are the strings derived from context-free languages? Those are also accepted by using the condition of acceptance of languages by pushdown automata. Now, how to define? So here there are two categories for acceptance of languages. First one is by reaching final state. Second one is by empty stack. So here without final state also, we can verify the acceptance of languages by pushdown automata. How this can be done? By using stack. So whenever input is empty, stack is also empty, irrespective of any state, next state. So the language is accepted by PDA. Suppose if stack is not empty, the next state is a final state as usual, same as in finite automata. Then the language is accepted by PDA. Now we will see one by one. Then some cases with combination of both also. So our next state, let us know final state. The stack is also empty. Then the language is accepted with both final state and empty state. That is also possible here. Now the first condition, acceptance by final state. How to define? See the definition. So let m equal to q sigma tau delta q naught z naught f. The 7 tuples be a PDA. A language L is accepted by PDA with the final state. First we will see the final state condition. E is defined as L of m as usual. In finite automata also same L of m equal to W. So you can take some string W from L such that now you can apply the ID. This is nothing but ID, instantaneous description. First you can take the initial or start state, then the input string, whatever the string we have considered here, then the initial symbol of the stack top, that is Z naught. By applying ID, Finally, by substituting all the transitions of the PDA, finally you will get a state P and input is empty and stack contains some stack contents, that is tau closure. Here you can see the condition for some P belongs to F. It's very important. Whatever the state here, this should be at least one state from P. P contains more than one state also sometimes. So that some P should belongs to a final state. Then whatever the stack, don't bother about stack here. Here we are seeing only final state condition. So then your gamma belongs to tau closure, that is stack contents. So in this case, we can say whenever this thing is accepted with this PDA by reaching a final state, then you can say the language is also accepted by this PDA by reaching final state. So that is the condition of acceptance by final state. Similarly, the second condition by empty stack. Here you can see acceptance by empty stack. The condition is so everything same here. The only difference you can see the definition is same. Let m equal to q sigma tau delta q naught z naught f be a pushdown automaton. A language L is accepted by a PDA with empty stack, also called as null stack. So which is denoted by n of m. Here n stands for null stack. So language accepted by final state by default denoted by L of m. But especially for empty stack or null stack, denoted as n of m. And defined as n of m equal to, here also take the string as usual w, then find out the ID. Here you can see from initial state q naught, the given string w, then the top symbol of the stack z naught, that is initial symbol. By applying ID, finally you will get some state p, input is empty. Then you can see here stack is also empty or null. So this is the condition needs to be satisfied. Here for some p belongs to q. Here we are not defining p belongs to f. P is any state. So but here stack is empty. That is very important. Stack is empty or null. So then only we can say the string or language is accepted by PDA with empty stack or null stack. That is the only difference. In case of empty stack or null stack, so we no need to bother about the state, whatever the state, but only our criteria is you can see the empty stack. So this is the condition of acceptance of languages by PDA with empty stack or null stack. Now combination of both here you can see acceptance by both final state and empty stack. That means both conditions needs to be satisfied. So here let m equal to q sigma tau delta q naught z naught f be a PDA. A language L is accepted by PDA with both final state and empty stack or null stack. See both conditions are satisfied. L of m equal to w such that q naught comma w comma z naught, the ID here you can see here equal to p, input is empty, stack is empty. So for some p belongs to f here you can see. So here p belongs to final state and the stack is empty or null. Then you can say both conditions are satisfied. In this case, we can say the language or string is accepted by PDA with both the final state and empty stack. Now next class, we will continue with one example problem followed by other topic.